This is an introduction to the topic of operational semantics, more specifically to the big step style of operational semantics. And before I continue, I should point out that I take for granted that you know about abstract syntax definition and also you have seen some form of interpreter before, because this is essential in understanding operational semantics. So a semantics definition overall, no matter whether it's done in operational style, is basically meant to assign meanings to language elements. And as far as today's presentation is concerned, we use this running example here, a simple expression language with constant forms of expression true, false, zero, and then constructs like suck and pred to compute successor and predecessor of natural numbers. We also have a construct is zero for a test for a natural number to be zero and to return a boolean. And we have an if and else. This expression language, we call it BTL for basic tuple language, where a tuple refers to Peirce's textbook types in programming languages. Alright, so a big step operational semantics definition is essentially a rule-based definition of the relation between program phrases, such as expressions in the case of BTL, and execution or evaluation results. These are values in the case of BTL. Typically, we have one rule or sometimes several rules per language construct. So here's the rule or the axiom, as we say, for 0. 0 evaluates to 0. Here's the rule for a successor construct. That is, suck of e evaluates to suck of n if the argument e evaluates to n. So here we assume that e could be any expression and n is a natural number. More interestingly, we have two rules for pred, predecessor. The first rule is for the case that the argument evaluates to 0, in which case we say that the predecessor is also 0. And the second case, if the argument evaluates to a number greater than 0, well, then we take the predecessor indeed. So we use metavariables all over the place here in a way that e proxies really for any expression, whereas n proxies for a natural number. So here's a bit more about the general format for the inference rules that we use here. We say inference rules or deduction rules or just rules. So these rules consist of conclusion and premises. If we have a rule without any premises, then we refer to it as an axiom. Typically, we attach labels to rules for ease of reference. So we read these axioms in a deductive style. So basically we say, in order to conclude that C holds, we need to establish that P1 to Pn holds. Within the conclusions and the premises, we make relationship claims. We relate, in the case of BDL, we relate expressions and values. The format for these relationship claims, we also call it judgments. So we might use a very nice to read prefix notation. For example, for BTL, we might say E evaluates to V. Or as we did before, we might use this mixed fix notation, which is maybe more suggestive of the computational interpretation at hand here, that we assume that E is evaluated to V. But it's really just an alternative notation for relation. When we have a more complicated language, let's say an imperative language, the judgment would also involve a store for the verb assignment, of the store before the execution of the statement M, and the store after the execution M prime. Or if we had a more complex language in the sense of a functional programming language, then expression evaluation would also need to refer to function definitions that may be applied within E, and also to an argument context M due to argument bindings within function applications. So I already said a few words about metavariables. So here we have all the metavariables again for the BTL expression language. So we've got expressions, E, natural numbers, and booleans, B, and values, V being either booleans or natural numbers. So the idea is that we use these metavariables carefully throughout the inference rules. So this is quite important. So for example, here within the premise, when we say e evaluates to n, we actually constrain what kind of result we need here. So a Boolean value would not be acceptable here. So e is really potentially any expression, but n must be a natural number. This is in the interest of constructing a reasonable successor result here, a reasonable natural number. Okay, so here are all the inference rules for the BTL expression language. I also highlighted those rules that we have seen earlier, so let's just quickly go through these rules one by one. So obviously true evaluates to true, false evaluates to false, and zero evaluates to zero. We have seen suck, how we basically evaluate the argument and then indeed construct the successor. We have seen the rules for pred, where we also evaluate the argument and then we might access the predecessor if available or not. Now here are the two rules for the zero test, where we essentially map a natural number to a Boolean value. So when the argument evaluates to zero, we return true. When the argument returns to non-zero, we return false. And here are the two rules for the ifs and else. And of course, we assume that the condition evaluates to the Boolean value, and depending on whether it's true or false, we continue, so to say, with either the then branch or the else branch. The way how we apply the inference rules to a given initial judgment can be represented as a tree, as a derivation tree. So here we show the proof of the judgment that this complicated expression, pred, if, etc., evaluates to zero. So the proof in this tree-like shape basically just applies inference rules systematically. So here we see that the outermost construct is pred. So we need to determine the appropriate pred rule, which turns out to be pred2 here. And pred2, well, this means we are looking at the argument of pred, which is an if. So again, we need to determine appropriate if rule, and this turns out to be the if rule for the condition to be true. And this part of the tree here is concerned with evaluating the condition, and this part of the tree is concerned with the evaluation of the then branch. So the idea is that we build this tree just by instantiating inference rules. So we can also map inference rules to Haskell very easily. So here I show this for one rule. So you see how basically the expression part of the judgment from the conclusion ends up here on the left hand side, and the result part of the conclusion ends up here on the right hand side of the equation, and also how the premise ends up as a pattern guard to the equation. And then here's some initial type check on the result of the premise. So we need to check that indeed we've got a natural number, simply because, of course, Haskell doesn't care about our metavariable conventions. So it's not enough in Haskell to write n to be sure that it's a natural number. Whereas here, by convention, we mean exactly that. All right, so here's the complete interpreter where we mapped all the inference rules for BTL to Haskell. I think it's pretty clear that it's a very systematic process. So in fact, the mapping that we apply here, but it's not the only mapping that exists, is such that one inference rule becomes exactly one equation. Another thing is this interpreter may be undefined when we apply it to certain kinds of terms, such as, let's say, is zero true? In this case, there would be no equation. So there's alternatives for encoding the inference rules so that we maybe not see an undefined, but rather we return a maybe. Okay, let's also look at a more complex example. Let's look at the semantics of simple imperative programs. So in the Softlang book, we call the corresponding language BIPL, basic imperative programming language. And here are all the metavariables and corresponding types. So of course we've got statements and expressions. Within the expressions we have unary and binary operators. We need variable names, these are strings. We have integer values, boolean values, and we need to represent stores, that is variable assignments. These are collections of variable name value pairs. So the major judgments that we need is that indeed a statement as is executed, starting from store m, resulting in store m prime. And when we have an expression, it's evaluated to a value v, while we may observe the store m because variables may occur within the expression e. Alright, so here's the statement execution part. So in an empty statement, skip, just doesn't change the store at all. When we have an assignment, we of course need to evaluate the right hand side expression to some value v, and then we need to modify the incoming store m to return v at a position x, which is the left hand side variable of the assignment. When we have a sequential composition, we just execute both statements while we pass around the memory from left to right, so to say. And there are two rules for ifs and else, very similar to the ifs and else of BDL. And here is an interesting semantics of the while statement or while loops, where we basically say executing a while loop is like executing an if statement where we test for the same condition as in the while loop. And if the condition holds, we first execute the body once, followed by the while loop again. And if the condition didn't hold to start with, then we just have the empty statement in the else branch. So expression evaluation very briefly. An int constant evaluates to itself. When we have a variable, we look it up from the store. When we have a unary or binary expression, then we need to evaluate the arguments. And here we assume some auxiliary relations, unary underlined, binary underlined, that know how to apply certain operators to certain values. We don't show the details here, they are pretty boring. So let's also look at the semantics of a simple functional language. So this is called BFPL in the Softlang book, Basic Functional Programming Language. And here are all the types and the metavariables. So we've got programs. Programs are essentially lists of function definitions with a main expression. Functions, well, these are function collections or lists of function definitions, and each function consists of a signature. This is essentially the type of the function. And the right hand side of a function is an expression. Just like in BIPL, we have operator symbols, and here we have argument names and function names, x. We have integers, booleans, values, and environments. These are collections of argument name value pairs. So the central judgment is that we have an expression and we evaluate to a value, but we might see some argument bindings m, and we might also see the function definitions in case we apply them within e. So here's the first part of the judgment for expression evaluation. We only left out the semantics of function application. So again, like constants, just evaluate to themselves. When we encounter the argument of a function, we just look it up from the context, from the environment. There are two rules again for ifs and else, pretty much like we have seen it before. And there are also two rules for unary and binary expressions. The function application is defined here. So we've got a name of a function to be applied. We've got a list of expressions for the actual arguments. And so we go first here and evaluate all the arguments. Then we look up the function in question from the list of functions. So we know the name of the function, and so by this lookup we also get the list of the formal arguments of the function, x1 to xn. The signature, the function type, we don't care much about here in the semantics. That would be part of a type system, a type checker, that we would look at it. And e here is the body of the function. So what we do is we evaluate the body of the function, the right-hand side if you like, and we pass the function definitions as before, but we construct a new environment here that we map the formal argument names to the actual argument values. So that's it. All the code for the implemented semantics definitions is online. This concerns the languages BTL, BIPL, and BFPL. There is actually Haskell code and Prolog code and also code in some other languages possibly. And this topic is covered in a software languages book. And we discuss not just big step semantics there in more detail, we also deal with small step operational semantics as well as denotational semantics. Thank you.